Here's the way I remember the trapezoid formula. If you think of a trapezoid as basically a triangle, but you kind of split it up here. It's like a triangle with an extra base in it. So if these were to go in, it would be that. If these were to go separate out, you create that base one, that top base. So this formula is exactly the same. Just a minute. This formula is exactly the same as it is for a triangle. It's 1/2 base times height. It's just that a trapezoid has 2 bases. That's it. Yeah, David?
Yeah. If it's a right triangle, do you have to divide by 2?
Yes.
You already have the height.
Yes, but you still have to divide by 2.
No matter what, there's no.
It's just in a right triangle, the base and the height are the legs of the right triangle.
So there's no section.
No section. So here's a sample problem. Our neighboring state, Nevada, actually looks like a trapezoid. You might have to tilt your head sideways to see it. Do you guys see the trapezoid up there?
Yeah.
Turn your paper. So this is why I like Nevada. It's got a lot. That's part of it. It's got lots of square mileage, and guess what? A lot of the square mileage is BLM or just open land that you can. Like I could take my dirt bike if I wanted to, and I could ride from here to here and not go on any roads. There are routes from there to there in Nevada.
You should do that.
I've done part of it. Just this little section up here I have before, but maybe 125 miles of it. But Nevada has a lot of square mileage. Now, you see why putting the units on these problems is important for a problem like this? I mean, we're talking about. I have to stop again. One of you will have to move. Square mileage here. So let's go ahead and plug into our formula. We have area equals 1/2 the height, base 1 plus base 2. So we just need to identify the height, base 1 and base 2. So what is the height here? What is the height?
5'11".
Height isn't 5'11", not the way it's
For which one?
for this trapezoid. Height's not 5'11". You got to take this trapezoid and rotate it
Oh, yeah.
90 degrees. It's 309 for the height. See why transformations, being able to see transformations is important. It's a trapezoid that's been rotated 90 degrees. So base 1 we would call the 205 usually, the smaller one, and then base 2 would be the 5'11". I'm going to go ahead and add together the 205 and 511 to get 716. And then on your calculator, go ahead and punch that in. Somebody got a calculator handy?
221,260.
Yep, and then you got to divide by 2.
110,622.
What number is that? 110622.
100,000.
A lot of square mileage with lots of dirt bike riding.
Wait, what's he going to You know, except for the buildings. You can't really ride on those.
There aren't too many of those in Nevada either. It's pretty wide open.
Why like a part of the country?
I don't know. That's just how the picture came through. So 110,622 square miles.
Should write that.
Now, example 2. I'm going to ask you, this time I'm going to give you the area and 2 of the 3 variables on the right and ask you to solve for the other variable. So this involves a little bit of algebra. Let's go ahead and plug in what we've got here. The area of the trapezoid is 20, so I'm going to put 20 in for A. And when I do, when I substitute in a number for a letter in an algebraic substitution, I put it in parentheses. So that's why I have the parentheses around the A. I'm showing you that I'm replacing A in our formula up here with 20. 1/2 is in the formula. Am I given the height? Looks like I am. Height is 4. And then I'm also given base 1, this base right here, as 4. So I'm going to put parentheses around the 4 as well. And then these are the parentheses that come in the formula. So I've plugged in everything I know, and the only variable I'm left with is B sub 2. The second base or the bottom base. So if I were to draw a picture here, I have this trapezoid with an area of 20. It's got a height of 4. It's got a base 1 of 4, and I'm going to find the second base. So, what would you guys do first in solving this algebra problem?
First, you would multiply 4 times 4 for the square.
You could. You could. If this is an even number, though, I'd just take half of it now. Yeah, I'd write down 2. Then you'll just have to distribute the 2. So you have 2 choices here. You could distribute the 2, or you could divide by 2. How many of you would distribute the 2 first? I would guess probably most of you would. Yeah, we're always thinking distributive property, usually coming from algebra. It's not hard to divide by 2 here either. But sometimes dividing by this number right here will create, yeah, I probably would in this one. But if this were, say, a 15 over here, I probably wouldn't divide by 2 because you'd get a 7.5 or something. So it depends. That's fine, yeah. Let's go ahead and distribute. Since most of you would do that. Subtract the 8 over. 12 equals 2, b sub 2. Yeah, if you don't like the subscript, you can just call it x. And then divide by 2. 6. So b sub 2 equals 6. What are we talking about on units here? Here's where units matter.
Centimeters.
Centimeters, not square.
Not square because it's the length.
Yeah, we found a one-dimensional length. Yeah.
Round would also work. The way I did it, you take the square, and then with whatever you have left over, you plug into the length, and you divide by 2, then plug into the length.
You turn it into a
There's 4 left,
rectangle,
and then I divided by 2, and then I plug that in as the length 4. So like,
how it works.
Seems more complicated.
would that always work? Or just for the problem?
I think that'll work. If I'm following you correctly.
Yeah.
I think so. Alright. So any questions on this? This is probably the hardest example, is solving for one of the bases in the trapezoid formula. But you need to be able to do it. You need to know the trapezoid formula as well. You have to have it memorized. Alright. For a rhombus or kite, if you know the diagonals, and this is a new formula. If you know the diagonals, you can find the area by taking 1/2 diagonal 1 times diagonal 2. Okay, if you know the diagonals. Pretty useful formula. Looks exactly like the area formula for a triangle, right? I mean, it has the same form.
That's around. This is the formula.
What is the length of it?
The length of the what you need for E2, what you need left for E2, and you add that to the E1.
What's the other thing on the other side? That's their length.
What this?
These numbers are places.
That's the.
Yeah.
That's the.
You need to move them to match up with mine.
That's real.
Oh yeah, this is the old one. Oh no. Didn't record it. That's a bummer.
Wait, which one?
Yeah, I totally redrew it. Moved the numbers. The numbers should be 5, 5, and 13. The numbers didn't move with the shape. I'll have to look at that later, dude. You have to show me a picture. So, with these particular numbers, can you find the lengths of the diagonals to be able to use this one? Sure. What's the length? What's this length here? 5. This is a right triangle. So what is this length here?
Pythagorean.
Pythagorean theorem. Or this is a triple. This is a triple. It's 12, yeah. You should recognize the 5, 12, 13 at this point. It's a triple.
I do.
So the area is equal to 1/2 diagonal 1 times diagonal 2. What's the length of diagonal 1 here? The short one. 10. And then diagonal 2? 17. So the area equals 170 divided by 2, or 85 square units. So as opposed to finding the area of one of these triangles, Right, I'd find the area of this triangle, double it, find the area of this triangle, double it, add those all up. That was how we've done it before. So a little easier to do if you know the diagonals.
Are they usually going to be triples?
On a lot of these they are, yeah. But if it's not a triple, you would just use the Pythagorean theorem and probably leave it in that. But I like triples. When I make up problems, they'll probably be triples. Because then we don't have to do the calculation of the Pythagorean theorem. I'm just testing on area of that shape instead. All right, number 4. Go ahead and plot this rhombus. I'm going to see you plotting this rhombus here. Number 4, you're on the wrong page. Plot the rhombus, and then I'll tell you what I want you to do after that. Is it really a rhombus? How would you check to see if this really was a rhombus? It is. It's kind of a different looking rhombus. But is it really a rhombus?
Rhombus would be rhombus.
Nope, that's a square. It is. It is. It's got some special characteristics. So do you guys remember what's special about a rhombus?
And it's like, it's just this, and then it goes like this.
That's true. That's true for a parallelogram. So do you guys hear what Emily said? The two opposite angles are congruent here, but that's true just for a parallelogram. Rhombus has something special about it. We have over here we have the rectangle that has all angles equal. Over here we have the rhombus. No, the diagonals are perpendicular. That's true. No, it has to do with the sides of the rhombus. I don't know if you can tell. Yes, that's what's true. So the sides are equal. You said the opposite angles are equal. Opposite sides are equal, but that's true in any parallelogram.
Yeah,
So
that's good.
all 4 sides are equal here. Now look at this. If I were to use, okay, don't do this, but if I were to use the Pythagorean theorem, this is 2 by 4. This is 2 by 4. This is 2 by 4 and 4 by 2. So no matter what I did, I would end up with the same length when I square 2 and I square 4 now. I'm not taking square root. So it is a rhombus. Otherwise, I wouldn't call it that. What you need to do is find the lengths of the diagonals. Any ideas on how I would find the lengths of those 2 green diagonals right there? This goes back to last chapter. 2 chapters ago, sorry. The whole trig chapter. We learned 3 things in the trig chapter. SOHCAHTOA, sine, cosine, tangent step, special right triangles, and Pythagorean theorem.
So we would have to get more than 5 4 times.
Yes. The Pythagorean theorem would help us to find the lengths of these diagonals. So watch this. You got to watch carefully on this. So from this vertex right here, A. Jessica, you need to go ahead and move here. Or actually, one of you. You or Bailey, doesn't matter. Right up here is. See, that's right. So one of you can decide. But if I start right here at A, I'm going to go over 1, 2, 3, 4, 5, 6, and up 1, 2, 3, 4, 5, 6 to get to D. So what are the legs of that right triangle that have this as its hypotenuse?
So it's 6 by 6.
6 by 6. So AD is equal to the square root of 6 squared plus 6 squared. So that's by the Pythagorean theorem. I can find diagonal AD by taking the square root of 6 squared plus 6 squared. So 36 and 36 is 72. So I have square root of 72. If I want to, I could simplify it. I don't know that I... Oh, you have a question? Let me show you here with the dotted lines here. I go over... Because the Pythagorean theorem says AD squared will equal 6 squared plus 6 squared. So the reason I square root it is to solve for AD. If AD is squared here, to get AD by itself, I have to square root it.
Just put it different.
Yeah, call it C. And that gets confusing because I have a point C and length C. Now, we could simplify this by doing a little factor tree and stuff, but think about what we're going to do with this diagonal. What are we going to ultimately do with the diagonal? Find the other one and then multiply them together to get the area, right? So let's just wait until the end to simplify.
Wait.
No.
That wasn't good. There was like a lot of.
We're going to leave it as square root of 72, the exact value.
Oh, okay.
Okay, so BC, what is BC equal to? Let's see if you can tell me what the,
2 by 2.
yeah, 2 squared plus 2 squared. As a matter of fact, we could have used special right triangles on this. Huh?
Wait. How do you, whoa, what is it? How do you get that?
The 2 and the 2. From point C, I go over 1, 2, and up 2 to get.
No, you go to wait.
What?
You just go to point. Oh.
Because I'm using the Pythagorean theorem to find the length of BC, which is the hypotenuse of that little red triangle in here.
Square root of 8.
So this is the square root of 8. That's right. So,
Square root of 8.
does anybody see another way to do this using special right triangles? Did anybody pick up on that? This is a special right triangle. If this is 6 and this is 6, what would AD be? That's 45. What would AD have to be? 6 root 2, yeah. Guess what this is equal to when you simplify it?
6 root 2.
6 root 2, yeah.
Oh, no.
So, my area is 1/2 diagonal 1 times diagonal 2, or 1/2. Diagonal 1 is square root of 8. Diagonal 2 is square root of 72. So if you do 8, go ahead and multiply 8 times 72 together. And then we need to simplify it. What is it?
750 or 576.
576?
Where?
And then you square root that.
Yeah.
Now we have it.
This is 24.
Good. So 576, the square root of that is 24.
And then we have it.
Then you take half of that. You get 12 square units. Good. In the homework, it's going to ask you when you do these problems to leave it in simplified radical form. Okay, so we know what that means. Yeah, this one happened to come out as a perfect square, but
But if it doesn't, then you just leave it.
yeah, like with the root 2 attached or whatever.
Wait, I reached that.
Oh,
So-
you just do 2 and then square root.
Yeah, you might get down to this stage and have to do the factor tree or whatever.
It's a lot of work.
Any questions on it? We always